right, good morning or good afternoon, advanced algebra. Hopefully, you're watching this after you've completed the first part of the investigation and you're wanting to work through the proof. So, the idea for the first logarithm property is that if you have the sum of two logs such that the base on the two logs is equal, then you can combine the two logs by multiplying the arguments. Okay, so log of x plus log of y is equal to log of x times y. And so you can use that to solve log problems without a calculator that you previously hadn't been able to. So what I want to talk about is why that's true. And it's the proof for why this property happens. Okay, so logs are pretty much like exponents, right? They undo exponents, so so that means that they're really closely related to properties of exponents. Do we have a property of exponents that relates to adding? Like, is there a property of exponents that can we add the exponents? Okay, and there is. It's when we're multiplying the bases. So it's kind of like that exponential property, but in reverse. So that's what we're going to use in our proof. So what we need to say in our proof is our given, and then what we're going to try and say. Okay. Oops, a little blurry, sorry. There we go. Okay, so our given, we just need to be given two different logs, and I'm going to label them with some different variables. So m will equal log base a of x, so that's our first variable, or our first log, and n will equal log base a of y. Okay. The reason we're going to use m and n is it'll make our work cleaner if we can just say it with m and n instead. Okay. What we're going to try and prove is that log base a of x plus log base a of y is equal to log base a of x times y. Okay. I know I just saw when I wrote it in our packet it says b and I'm using a in our proof, but it's the same thing. All right, so we're going to do a two-column proof for this. I know in geometry you guys did various styles of proofs. I like two-column. Okay. And so we're going to start with the given. Okay. So it's m is equal to log base a of x, and n is equal to log base a of y. The reason one is given. Okay. Well, what can we do with these things? Not much other than switch forms, right? They're given in log form, so let's switch it to exponential form. The first one would be a to the power of m is equal to x, and then this would be a to the power of n is equal to y. So the reason we can do that is it's the definition of log, or definition of logarithm. Okay. Next, what we can do is multiply these things together. So essentially what I'm going to do is take this first equation, a to the m equals x, and I'm going to multiply it by a to the n on both sides. But since a to the n is also equal to the y, I'm going to write y on one side. Okay, so a to the m times a to the n is equal to x times y. Okay, so what I did was take the first equation and then I just multiplied it by the same thing. Okay. If these two things are equal, it's like you're multiplying by the same thing on both sides. So that is the multiplicative property of equality. Okay. Step 4 is, well, these two things have the same base, so we can add our exponents. So it's a to the m plus n is equal to x times y. And so that's where we're seeing the big connection with where this log property is coming from. Okay. Is when you have bases that are the same, you can add the exponents. Okay, so that is called the product rule of exponents. Our next step is to switch it back into log form. Okay, we have this base with an exponent, and then it equals xy. So to write it in log form, it would be log, and then our base is a, of the argument x times y, and then it equals the exponent m plus n. So the reason we did that was the definition of log. We switched it from exponential form to log form. Okay, I bet you can see what our last step is going to be. Okay, we are almost to our proof step. Okay, we have log base a of xy. We just need it the other side to say log base a of x plus log base a of y, which we know m equals log base a of x and n equals log base a of y. So by substitution, we're there. Okay, log base a of xy equals log base a of x plus log base a of y. And the reason is substitution. Okay, and that's it. We were able to prove our first property. Okay, from here, I'd like you to continue and work on the second part. And I'll give you a hint that that proof is pretty much the same as the first one. Okay, so go ahead and pause this video right now. And then when you're ready, you can check the proof for that second one. Okay, so you should have completed the second part, which part 2 says if you have the difference of two logs, the way to combine them is to divide the arguments. And the proof for that should look something like this. So if you need to, go ahead and pause this video so you can check your work, but it's really the same thing that we did before. You're using the definition of log to write it in exponential form, but instead of multiplying, you would divide. That would allow you to subtract your exponents, write in log form, and then by substitution, you've got your property. Okay, so on to part 3. Go ahead and complete the first part of part 3. And when you're ready, we'll talk about the proof for that. Okay, so for part 3, I know I wish there was a more clear way of having you investigate this. So if you have a suggestion, I am all ears. But the idea is when you have an exponent inside a log, that is equivalent to bringing that exponent out in front and making it a coefficient in front of the log. C times log base b of a. Okay? So for example, with number 19, log base 5 of 5 squared is the same thing as 2 times log base 5 of 5. So our proof for that is the one where it's the power of a power, you multiply. So it's related to that. I want to show you the proof. So we're going to let m equal log base a of x. And I'm just going to abbreviate our work a little bit. Our first step, like normal, is just switch forms. So it would be a to the m equals x. So that is the definition of log that allows us to write that. So it's the base of a to the exponent of m equals the argument x. From there, we're going to raise both sides to some power. Okay, you can choose whatever letter you want. Sorry, lights turned off. Okay, there we go. I'm going to use n, so a to the m all to the n equals x to the n. Okay, so the reason we're doing that is we're going to raise by n on both sides. On the left-hand side, a power to a power, you can multiply. So a to the mn equals x to the n. And that is the product rule of powers. So now the next step here is kind of tricky because we do want to write it in log form, but we have bases with exponents on both sides. So which one is it gets to be the base and which one gets to be the exponent? You know what I mean? So, or the argument. We're going to have the side with the a be the base. Okay, so I'm going to put boxes around these just so you can see what I'm saying. The a is the base, mn is the argument, and then, or exponent, x to the n is the argument. So in log form, it would be log base a of x to the n, and it equals m times n, the exponent. And the reason is definition of log. So we're almost there. Log base a of x to the n equals m is equivalent to log base a of x. And I'm going to use the commutative property of multiplication at the same step as well and just write n in front. So n times log base a of x. So two reasons here, the commutative property of multiplication and substitution, because we know what m equals. We could substitute that in. So this property with logs is related to the product of power rule with exponents. So there are three big properties of logs that I want you to summarize from this packet. The first one is the product rule, which says if you have the sum of two logs, you can combine them by multiplying the arguments. If you have the difference of two logs, you can combine them by dividing the arguments. And then if you have a power within a log, you can bring that power out in front and make it a coefficient. So it's b times log of a. All right, so once you have that, I want you to, for homework, work on this last page. Okay? Thank you.